Hey class! On the worksheet you completed on Friday, you met the concept of the kernel of a homomorphism. And if you had the chance to try the challenge problem on that worksheet, you also began to get the sense that the kernel of a homomorphism has something to do with whether that homomorphism is injective. In today's video, I'll start by reiterating the definition of kernel, and I'll also add to it the notion called image, which we'll see is related to whether the homomorphism is surjective. Here's those two definitions. For these definitions, we'll let phi from G to H be a homomorphism from a group G to another group H. Then, as we saw on the worksheet, we'll define the kernel of phi to be the set of all G in the group capital G such that phi of G is equal to the identity. Notice that that's a subset of the group G, in other words, the domain of the homomorphism. The image of phi, on the other hand, is defined as the set of all H in the group capital H that are phi of something. In other words, it's the set of all H in the group capital H such that H is equal to phi of G for some G in the group capital G. Notice that this is a subset of H, in other words, of the codomain of phi. To put these definitions in words, the kernel of phi is what phi sends to the identity, and the image of phi is sort of what's hit by phi. Let's look at a schematic picture to see kind of what this looks like. If I denote the elements of G by these blue dots on the left and the elements of H by these green dots on the right, then a homomorphism phi is a function from G to H, so I can denote it schematically by drawing some arrows from left to right, maybe something like this. Now, one of the elements of H is the identity element. Let's say it's this top dot here. And then the kernel of phi consists of all of the elements of G that are sent to the identity. So those are the three dots that I've circled in yellow here. Whereas the image of phi is all of the dots on the right that have an arrow going to them, which is the two that I've circled in yellow on the right. So that's a schematic picture. Let's now look at a specific example to get a sense of what this can look like in practice. Let's think about the group Z of integers where the operation is addition, and the group R star of non-zero real numbers where the operation is multiplication. Then I can define a homomorphism phi from Z to R star by the formula phi of n is equal to -1 to the nth power. So that means phi of 1 is equal to -1 to the first power, which is -1, and phi of 2 is equal to -1 squared, which is 1. Phi of 3 is equal to -1 to the third power, which is back to -1. And in general, what you'll notice is that phi of n is either going to come out to be -1 or +1, just depending on whether n is odd or even. So what are the kernel and image of this homomorphism phi? Well, the kernel consists of all elements of the domain, so all integers, that are sent to the identity element of R star. Now, what's the identity element of R star? The operation over there is multiplication, and so its identity element is 1. In other words, the kernel of phi consists of all of the integers that phi sends to 1, and by the argument that I've just made aloud, that's exactly all the even integers. How about the image of phi? Well, that's all the elements of R star that are phi of something, and phi only sends anything to either 1 or -1, so the image of phi just contains those two numbers, 1 and -1. So that's the idea of what kernels and images are all about, and you'll practice with some more specific examples in your worksheet for today. But the last thing I want to do in this video is tell you, as I alluded to at the very beginning, what the connection is between kernels and images on the one hand and injectivity and surjectivity on the other hand. So here's a theorem that makes that relationship precise. The theorem says, let phi from G to H be a homomorphism. Then there's two statements. First of all, phi is injective if and only if the kernel of phi has just one single element in it, and that single element is the identity element of the group G, which I'm denoting E sub G. And part two, phi is surjective if and only if the image of phi is the entire group capital H. So we'll now prove this theorem, and to prove it, we're going to need two facts about homomorphisms, which I'll state on the next slide. Fact number one that we need is that for any homomorphism phi sends the identity element of the group G to the identity element of the group H. We won't prove this fact because you may remember we proved it in the case where phi is an isomorphism, and if you look back carefully at the proof we used in that case, you'll see that actually the same proof applies to homomorphisms. We never used the bijectivity of phi in our old proof. And the second fact we'll need is something that I've asked you to prove on your next homework 10, which is that for any homomorphism phi and any element G in the domain of phi, if we do phi of G inverse, that's the same thing as doing phi of G and then taking the inverse of that. So keeping these two facts in mind, let's see how we prove the theorem. We'll actually start with statement number 2 because that's the easier one. So recall, statement number 2 of the theorem was that phi is surjective if and only if the image of phi is equal to the entire group H. But actually, this is true just straight from the definition of surjectivity. In particular, remember that the image of phi, by definition, is what's hit by phi. But on the other hand, being surjective by definition means everything in H is hit. So phi is surjective if and only if its image is all of H. So with that done, let's now turn to the first part of the theorem, which was the one that related injectivity to the kernel. That one's a little bit trickier. So recall, our goal here is to prove that phi is injective if and only if the kernel of phi consists just of the single element, e.g., the identity element in the group G. This is an if and only if statement, so we're going to divide the proof into two halves. First, we'll suppose that phi is injective and try to prove that the kernel of phi contains just this one element. Well, remember, fact number 1 above said that phi of EG is equal to EH, meaning EG is something in the domain that's sent to the identity. So EG is certainly an element of the kernel of phi. Why is it the only element in the kernel of phi, though? Well, to prove that, let's just pick a random element from the kernel of phi. I'll call it lowercase g. By definition, if lowercase g is in the kernel of phi, that means that phi sends lowercase g to the identity element in the group H. But as we've just seen, another thing that goes to the identity element in the group H is the identity element EG in the group G. But that means that phi of G is equal to phi of EG, and by injectivity, that's only possible if G and EG were the same to begin with. This proves not only that EG is in the kernel, but that it's the only thing in the kernel, because a random other element of the kernel turned out to just be equal to EG. So we're done with that half, that implication, and we can turn to the second implication in the proof of part 1 of the theorem. For this implication, remember what we need to do is we need to suppose that the kernel of phi contains just the identity element eg, and our goal will be to deduce that phi must be injective. Well, how do you prove that a function is injective? By definition, what you should do is you should start by assuming two elements go to the same place. Let's say phi of A is equal to phi of B. And after some argument, what you should hopefully find is that A is equal to B. In our case, the way we can get there is first by rearranging, in particular multiplying both sides of this equation by the inverse of phi of B. That'll move that phi of B inverse over to the left-hand side, and then on the right-hand side, we'll be left with just the identity element EH. Then using fact number 2 that we stated earlier, we can pull that inverse inside of the phi, and using the definition of a homomorphism, we can combine the two terms. So the left-hand side becomes phi of AB inverse. But notice this says phi of AB inverse equals the identity. So in other words, it says AB inverse is in the kernel of phi. And we've assumed that the only thing in the kernel of phi is the identity element eg, so AB inverse must be equal to that, which, if we multiply both sides by b, gives us A is equal to b, so we've supposed that phi of A equals phi of b, concluded that A equals b. That means exactly that phi is injective, and that finishes the proof of the theorem. So that's it for today's video. More practice to come on the worksheet for today's class, so I'll see you there.